Hello and welcome to Source Decode, your magic decoder ring to demystify the jargon surrounding the technology industry. I'm your host, Ben Coffin, and join me each week as I try to dig into what these buzzwords are all about, how they're being used, and who actually needs them. We're back with part 2 of our digital twin deep dive, in which I'm trying to understand what a digital twin is and what impact it's going to make to the everyday tech nerd like myself. If you missed part 1 of this series, why don't you head on over to keysight.com/find/source-decode and check out episode 4, where I talked to Dr. Rajiv Bagrodia about where the term digital twin comes from and how it's being used to revolutionize the way we plan, test, and secure networks. Now, while you're over on the site, hit that join our mailing list button to get a digest of what's happening in the world of Source Decode, including bios on our host, extra content around our season's topics, and you can be entered for a chance to win a Source Decode hoodie, so you can show off your love of the show and stay comfy while doing it. Now, again, you can find that link in our show notes, or you can just head on over to keysight.com/find/source-decode in your web browser. Today, we're looking at digital twins in a different light than last week. If you went through any type of STEM education, you're probably familiar with the process of doing some modeling or some simulation. When you're building up a model of an equation and plotting its results, or you're designing a circuit or a mechanical system, you press play to see if it does what it wants, and that result is a key step in learning in the STEM world. That process continues out of the classroom and into the world of product development, where the first step for every new product is to pull up your last version, wipe the slate clean, and start building new features. If you think about your cell phone, every new version comes with new functionality, new capability, and reasons to make that upgrade. Every one of those features didn't exist on the last version and has to be designed and integrated into how the system will work as a whole. So, how do you go about incorporating a digital twin? How does the digital twin change this workflow, and what does it mean to be using a digital twin in the design process? To find out, I sat down with Dr. Ian Rippke, Software Solutions Engineering District Manager at Keysight. Ian has over 15 years of experience working in this world of simulation and design and can look at this problem not only from a place of technical expertise, but also with a business lens that helps reveal the so what impact to the everyday person. We'll be right back with my conversation with Ian right after this.
Do you like podcasts about technology?
Like hearing from industry experts about the latest trends and developments in the world of cellular communications?
Want to stay up to date on the world of 5G and enjoy witty banter at the same time?
Then have we got a podcast for you.
I'm Dylan McGrath.
And I'm Jessica Vasos.
And we are the co-hosts of All Things 5G, the podcast that puts the G in 5G.
As in, gee, what a great podcast.
All Things 5G is the indispensable podcast for business leaders and engineers tackling the toughest 5G development and deployment challenges.
Each episode presents a deep dive into the technology, business, and policy issues surrounding a specific 5G topic.
Experts from Keysight Technologies and the industry at large serve as our guides through the evolving 5G landscape.
Check out All Things 5G on Apple Podcasts, Spotify, Google Podcasts, Stitcher, or whatever platform you use to get your podcasts.
All Things 5G is also available on the web at www.keysight.com/find/allthings5G.
Check it out today.
You'll be glad you did.
Well, hey, Ian, thank you so much for sitting down to chat with me. So we've got now, maybe our listeners have this idea of the notion of a digital twin. But if you stop to sort of look at the digital twin, you might start thinking, well, isn't that just like simulation software? Or isn't that, the sort of idea of a digital representation in the computer? So maybe let's kick off with, what's the difference between simulation and the digital twin?
Yeah, no, thanks, Ben. And yeah, great to be here and tackle this topic. It's one of those things that you could look back and say, well, yeah, we've been doing digital twins for decades, right? Simulation has existed. In fact, it's the only way we successfully build anything, pretty much in the electronics world today, is through simulation. But you're right; it's not really what people think of as a digital twin. So let's just talk simulation for the basics, right? When electronics got to the point where we were doing integrated circuits, especially these high transistor count, whether it's digital, analog, or RF. All of that pretty much requires simulation as part of the design process. And what people have always done is just assumed that, yes, simulation is my starting point. I'm going to run a whole bunch of simulations. And when I feel pretty confident or my schedule hits, I'm going to build it or, tape it out if it's a chip or if it's a more complex system. We're just going to put this thing together. There's still breadboarding and other types of rapid prototyping going on out there. But at the end of the day, the truth, the real truth of how that thing behaved was unknown until you built it, right? And that's where that was the prototype phase. So simulation was always in there. But I think one of the keys is that it was always considered an approximation. Right. It was a step towards an end product, but it was not a true representation of behavior.
Right.
You can go, especially you get into, some of the research and academia side, all kinds of arguments have been made throughout the years about the accuracy of simulation versus measurements. And particularly our customers out in the world want to see that correlation. They want to know that what they're buying as a simulator tool can get them as close to reality as possible. But I think that's where simulation has kind of lived for a long time. It is the best approximation that we can get prior to building something and getting the real answer, so to speak.
Okay. Yeah, and I remember that was always the thing in engineering school, and if any of our listeners went through the same process, it was always like, okay, we start our circuit in PSpice or some simulation software, we do it in MATLAB, and then we're going to get some idea of how it works, but then we get into the actual breadboard of it, and it's all of a sudden nothing works. None of this actually works once we've moved it into the real world. Well, why? And you had to figure out sort of that discrepancy. What you did wrong and what you didn't understand about a real component. So then, I guess for simulation, we're maybe familiar with that. On the digital twin side, what does that mean when we're then talking about the digital twin of a circuit?
Yeah, in my perspective, because I've lived in the simulation domain for most of my life. From being a student into supporting various simulation tools to the job I'm in now. The difference that I see is it has built-in correlation. That question, you can't have something be a twin if it doesn't actually predict or reflect reality. It's a reflection, but it's not an actual representation of what you're building. So this idea of, well, how does it become a digital twin, right? Let's take the simplest of situations, right? We've got an amplifier, and we've done all of our hard work and designed that thing, and then we've gone and produced it. Well, you could look at it and say, well, the simulation there, it's not the digital twin of the amplifier because we don't know whether the simulation results match the measurements. So then you take that next step and say, okay, well, I've built it. Now I'm going to measure it. Okay, I can measure things like noise figure, gain, IP3 or linearity, and I can start to take those and compare them to what I simulated. And if they match, great. That means I had good simulation models to start with. But let's say they don't match. Well, then what I want a way to take those measured results and update my simulation model. right? So that loop back, that's where we really start the process of creating a true digital twin, because now your model, your digital representation is actually linked or tracking what's being physically measured. And that's, kind of, they say, necessary but not sufficient. It's a starting point. Until you have measurement informed models, you can't even hope to have digital twins. But there's more to it than just that. Maybe we can get into that in a little bit.
Yeah, no, absolutely. That's interesting. So okay, so we start developing feedback from the real world back into the digital, and it's that sort of connective tissue back and forth that I think actually, as we start to look at this notion of digital twins, there is this sort of connective fiber that exists between both the real world and the digital, and that a lot of times is this data that's being generated, whether it be from measurements or from simulations or from tests or from measurement different types like that. It's all that together that actually gives us sort of that connective tissue. Okay, cool. So what about, we've got a circuit prototyped, right, that should be our be all end all, but then we also, we've given this feedback data back to the digital equivalent. We're going back to the digital. So why do we go back to the digital? And when I ask that, I think what I'm kind of saying is, like, what is it that we start getting when we start having this data informed digital twin that we can do with that the prototype on the breadboard doesn't allow us?
Yeah, great question. And it's one of the key things that people are looking to digital twins for. And as I see it, it's the what ifs, right? It's the exploration, because you can explore different architectures, circuit topologies, even different applications. If you start taking this broader into things like, well, how would this work if this was in a 5G communication system? Or how would it work if I was doing automotive vehicle-to-vehicle communications? These types of things are just very time consuming. They could be expensive if you're talking about like an aerospace defense application. You can't just easily say, I have a new radar transmitter. I wonder how that would work if I plug that into, my strike fighter. Okay, well, that's kind of expensive, right?
Right.
Put it in the system, fly that thing around, and you're talking. That's of course, kind of the extreme situation. But even just looking at how we use these components or these systems or subsystems, we can do so much more exploration digitally, or sort of in that virtual domain. And so that's where people are really getting interested about having that real world predictability and representation of their systems, because now they're not constrained by what they can test. They're just constrained by what they can imagine.
Interesting. And there's something there too with what you're saying about the subsystems or components, that it sounds like there can also be somewhat of a relationship between the digital twin and the real world, in up to a point where you say, hey, it actually doesn't make sense to prototype this entire thing. I just want to prototype a part of it, and then the digital twin can represent sort of the rest. Like, is that part of the workflow where you have kind of almost like hardware in the loop type of experience where there's a sort of a digital ecosystem around a physical prototype?
Absolutely. Some people look at digital twin and they think, I'm building a digital twin of a car. Okay, yes, that is one, digital twin that is going to be a very, very complicated system to try to build up.
Right.
But you can take that all the way down to, you could say, well, at the very basic level, if I have a really well characterized model of the wiring harness, well, that's effectively a digital twin of the wiring harness. And so at every level of component and system, you can do this. And then you're absolutely right. We almost need a new term, right? Twin in the loop or something like
Right.
that to
Hybrid
represent
twin or something.
where we're putting this stuff together. But yeah, there's a situation because these very few companies are fully vertically integrated anymore. So everybody's relying on suppliers and partners and other people in the design process. And what I think the digital twin offers, especially at the lower level, is a means of communication between these different companies and different groups. A simple example would be, that go back to that amplifier. Well, hey, I've got this new idea. I've done some performance improvements. Wouldn't my customers love to see how that would affect their designs without having to wait for me to start sampling that and send them examples, and they have to put it into their system? And again, it's a lot of this extra lab work. You start to have a currency, if you will, of intellectual property, and that is exchangeable, and hopefully at the end of the day helps everybody deliver better products faster.
Yeah, and that's actually super interesting because you think about this development workflow, right? And how it could be expedited. Like, one of the things that I think is maybe difficult for someone to come into, like, the concept of a digital twin and look at it, is go, yeah, but how does this actually help me, right? How does this help the everyday person? How does this help us with, whether it's consumer electronics or it's with our cars, or like, what is that? How does that advantage actually trickle down? And I think you started to tap into some of that with this idea that the supply chain, in concert with sort of the development process, can start to connect. But can you go into a little bit more detail on sort of like what this matters to the end user who may be completely unaware of this whole market ecosystem workflow?
Yeah, certainly. And I think, we, like you said, we touched on supply chain. There's benefits on either side of that, the consumer and the individual component developers. But let's tackle the consumer. The average consumer, especially in consumer electronics, commercial electronics, has zero interest in what's happening inside, as long as their next generation of whatever has more features or better battery life or better screen resolution, whatever it is, right? I very rarely have we run into a situation where someone says, that next generation product, please make it have less features than the one you have now. So,
Yep.
Of course, I'm being a bit glib, but the idea is that pressure and that demand in the market, and it's not just in commercial, it's also in military applications as well. We're always looking to squeeze more out of the next generation. So again, it goes back to that what if scenario that we talked about before. If you can do these what if scenarios accurately, and that they're going to represent what actually happens in the physical world when you build it, you open up a lot of doors that you couldn't have gone through in the past. Something as simple as, hey, this new chipset consumes 20% less power. Okay, well, that, to the guy doing the battery management, hey, great, that means the battery's going to last longer. But what if battery life isn't what the consumer wants? What if they want improved graphics, or
Right.
improved GPS tracking speed? There's trade-offs there that can be made, and say, well, yeah, I'm going to take that 20% battery savings, and that's going to let us put in a higher performance IC for GPS and connectivity, which is going to let us do more, or it's going to let us add in some additional frequency range support, or maybe it lets us do some active antenna type of capabilities. These are the trade-offs that the consumer will never see, but is going to benefit them because it means more features from effectively the same footprint or the same device performance they had before.
Yeah, absolutely. It seems like the speed at which we're able to move, like we start to think after a while, how can we possibly go faster than we already have been. That's something I've always thought, kind of seen in the engineering world is, every release, every version, everyone's time to market keeps getting smaller and smaller and smaller. And we think about like, how fast is it going to have to be till we release the next chip, and where's that going? But it does sound possible when we start talking about these ideas like the digital twin. There's a real, we can take both what we've learned from the last version and use that information again, right? We don't throw away everything and start over. We can actually recycle a lot of information. And on top of that, spend more time in the digital domain to get it right faster, earlier. And then this sort of simplifies things. I think it's really fascinating. This is a really powerful technology when you think about, like, at a certain point, Moore's law starts to get kind of like, can we really do that? So this is really cool.
Well, you touched on something there, Ben, that I want to just quick circle back to, which is we didn't get a chance to talk about, kind of the so what from the designer's perspective. So, because you look at it, and if I'm just a designer and I have to, build that amplifier. And now you're telling me, oh, no, you're not done. You've got to take that measurement data and you've got to make sure that that model is correlated and, that your digital twin matches the reality. First pass, it sounds just like more work, like, oh, and this is going to slow things down, right? This is, this isn't going to help me. But the advantage on the front end of this is, once you've gone through the process once and you have these digital twins of different pieces of your design or system, what that does is it saves you a tremendous amount of time in version 2, because you're not just starting from scratch. You're starting from basically knowing exactly what the performance of version 1 is. And so that speeding up that design cycle, absolutely, right? Companies out there have terabytes, petabytes of manufacturing data that's not being used to help inform the design of the next generation. Or military companies are putting out proposals, but they can't say whether their existing products could be partially reused or pieces of it could be modified. You're almost starting at square one every time.
Right.
You've got some new applications. So the digital twin, the first time through, it might take a little bit longer because you are needing to do some additional validation. But then every subsequent use of those models in the future speeds up the entire process.
Yeah, absolutely. Yeah, it's really interesting. If anyone that's ever done any sort of software-based creative effort, that how much templates help you. It's this idea of sort of, okay, once I've got it figured out and locked in, I can reuse it every time I go back to that. So it's that same notion for the circuit design process. That's so, it's going to change the workflow so much, it feels like.
Absolutely. Yeah. The way we define specifications for a product is going to completely shatter, right?
Yeah,
Where we right now say, hey, these are all the things we want it to do. Now go. I think it gives us that option to say, well, hey, here's what it can do now. So tell me what it could do if we make some of these trade-offs or these changes. It just that idea back to the what if, right? I think digital twins are going to help us turn the what if into the what is.
I like that. That's going to be in the show notes tagline right there. That's a good one. we better TM that. Well, cool, Ian. Thank you so much for chatting with me. I really appreciate it.
Yeah, fantastic. Thank you, Ben, for having me.
Sure about you, dear listener, but I'm having the opposite journey to digital twins that I had for AI. What I mean by that is when I started my dive into AI, I was a skeptic. I was seeing AI everywhere in hot marketing ads, and I just couldn't sort hype from reality. And then once I started to talk to people about what AI was doing, I became a believer. It became really easy to see why the hype was there. But with digital twins, I don't really see it used everywhere. Well, at least not anywhere but the tried and true markets where, people know about this technology. I see the term coming up, but I don't know if I really saw hype the same way that I did with AI. But then I start talking to experts like Ian and Rajiv, and all I can think about is, why aren't we doing more of this? I mean, let's take an example. We all know the impacts to the supply chain over the past few years have been a huge challenge for the tech industry. And when you think about how a digital twin could be used to get designs through the supply chain to your downstream vendors so that they can get started early before you can actually ship a part, I mean, that's every designer's dream. And maybe you're like me and you do some hobbyist projects, right? And, in my case, I build and I modify guitar pedals. And can you just imagine how great it would be if we had a digital twin of your project? I say I had a digital twin of my circuit on my computer and I could adjust on the fly. As I built, I got reaction into the simulation of what the simulation was doing, what the actual physical circuit was doing, and there was that tether between the two. Just looking at the digital twin workflow, I see so much promise, and it's really hard not to get excited. That's it for this week on Source to Code. Come back next week where we have our final episode on the digital twin series, where we're going to look at a different kind of digital twin and how it's impacting the world of self-driving cars. If you're enjoying the show and you want more of this kind of thing, please give us a rating on your podcast app of choice, or give us a follow or a subscribe. It helps us to know that you like what you're hearing. And of course, don't forget to go on over to keysight.com/find/source to code, where you can listen to all of our episodes and find links to the show on any of your podcast platforms and get the bonus content for each show. This week, we've got a solution brief called Creating Digital Twins of RF Systems, which breaks down how you can take a model-based approach to development and introduce the digital twin into your design. If you got excited about what Ian talked about for workflow, you've got to check out the solution brief. It is something I think you'll really enjoy. Thanks again to Dr. Ian Rippke for coming on the show. We had an absolute blast chatting digital twins, and there will definitely be a unedited, longer form conversation dropped in the off season where we can fit in all the things we quite couldn't pack into this episode. Once again, I'm Ben Coffin, and thank you for listening. This has been Source Decode.